Oh, the mic was switch off. Okay. Yeah. So we'll be starting up with autoencoders here. And so we'll be starting with structures of autoencoders, architecture of autoencoders, types of autoencoders, and finally variational autoencoders. So VAE, variation autoencoder, is a generative model where we can generate things other than which you already have in it. Okay. You'll be taking variation of the data which is already coming out. So it will be a new kind of data and hence the name generated coming into picture there. So in order to understand VAE, you need to understand what are autoencoders. So what's an autoencoder? Since we talked about it before also, your autoencoder is a type of unsupervised learning or is unsupervised neural network mainly used in feature extraction and dimensionality reduction. That's some two main important what functionalities of autoencoders. Okay, here we don't require label to represent some data here as we did it in classification. So in a classical MLP, that is machine learning model, okay, what do you do there? There are two components mainly. What are the two components? First, you do feature extraction. Based on that feature extraction, you classify. Do you remember that? In most of the machine learning algorithms, this is what you do. You extract the features first and then classify, or you give features as the input. The extracted features are input. Usually data engineers do that. Data engineers extract the features and keep it somewhere, and the scientist will come there and feed it to the neural networks, required neural networks with set parameters, and that will give the output. So MLP is not just using some machine learning algorithm. It's both feature extraction as well as classification or regression, you can say. Other than classification, we do regression also, but on extracted features. Okay, it's given you in a platter, that's well and good. Already cleaned up data is given to you with the labeled column, etc., etc., then it's fine. You will be happy and everyone will be happy. You can easily classify or do regression, but that's not the case. All data in the real world will have some or the other noise, some or the other distribution, and the major problem which comes into picture will be your pre-processing and data cleaning up. Okay, that will take more time than getting the end result itself. You don't clean the data, and if you don't give proper data or if you don't select proper features, then you won't get output at all. Or you might get a lower accuracy, which won't be required at all for a given application or a given project. So choosing proper features, pre-processing, data cleaning plays a vital role, then choosing a proper machine learning algorithm. Okay. So this is what we did till now. Now let's go into encoders. We know that in encoders, autoencoders, we mainly have encoder and decoder. What does encoder do? It compresses the data. It compresses the data to a latent space. We call the data, this is a latent space. Okay, this is called as latent space data. Original data to latent space data, from latent space data to approximate original data. Okay, this is what autoencoder is doing. Now you might question, why do you need to do this? You should talk in terms of applications. Okay. Why do you need to do this? Encode somewhere and decode somewhere. Yeah, one is dimensionality. Okay. In this example, which we saw, let's go to the practical example. Here you can see it, there are 784 units. They're slowly reduced to 20 units. From 20 units, again, they are reconstructed back to 784 units. Okay. If you already have a zero error, that is what you do. You train the network, test for something, and we see that my input image and the reconstructed image are nearly the same, means there is an encoder and a decoder. What do you do next? Keep encoder in India, take decoder to US. Okay. Encode the data, and instead of sending the whole image, just send 20 units. Okay. Instead of sending a whole film, just send some, instead of GB, send some in terms of MB. And in US, they will decode it. So what is happening? You're decreasing the bandwidth, yes or no? That's how your MP3, MP4, and even JPEG images work. You compress the data. Sorry? You can remove noise only. Noise also. What happens if you encode the data, encoder and decoder, if you know it, properly get an encoder and decoder based on the error. Okay. The amount of error. How is error calculated? Error is given by, sorry, mean square, absolutely right. That is, if x cap minus x, what does it mean? Difference between your input and reconstructed data. Okay, x cap is your reconstructed data and x is your original data. This is how error is calculated. We'll try to reduce as much as possible. After reducing the error, what do? There are parameters. There will be encoder parameter as theta and decoder parameter as some pi. Okay, we'll change these parameters in such a way that my error reduces to minimum. Okay, after reducing this error or the loss to minimum, you will give a noisy image to me. Okay, you will give set of noisy images to me. So what will I do? I'll take all these noisy images and provide the input. But at the output, I'll get a better image. Better cleaned image. Why? Because my network is trained in such a way to represent the reconstructed data which is similar to original data. So what does it do? It will filter the noise and give you the output, because that's how it is constructed. Okay. So some might think while transmitting bits also, usually they get corrupted. From transmitting from bits from India to some US, okay, corrupted. So how do you remove the corruption? No need to remove the corruption at all. Just pass through a decoder like this. That's enough. You will take care. Okay. So this is the advantage of auto encoders in terms of dimensional reduction as well as compression. Okay. And the same concept can be used for denoising also. 2-in-1. So let's get back. Okay. In principal component analysis, PCA, what was it doing? There also we are doing data reduction now. There also we are doing feature reduction. Okay, what was it doing there? It removes the correlated data, then it takes only uncorrelated data. Okay, similarly, here also, when you encode the data, the correlation is removed. Okay, and more wherever the energy is higher, energy of the input signal, it can be audio signal, video signal, or an image. Whatever, wherever the energy is there, only that is stored in 20 units. From 784, all the energy goes to 20 units. Okay, so that's how information travels. That's how we have got data here. This is data. From data, we are extracting information. Okay, you need only information. You don't need data. What is required? Information means what is required. So all the information is stored in uncorrelated data. That uncorrelated data is enough to reconstruct the original image. Okay, so this is autoencoders. So decoder reconstruct the input data from the latent space representation. This is the latent space representation A1, A2, A3. Okay, we call it as latent space data also. So it tries to attempt to make the output as close as possible to the original input. So when you did this assignment, you trained the data, no? What is the training? Training means making this error. Remove. That's what training is indicated there. Error reduce goes to minimum there, making that error to go 0 if possible. That's the ideal case. Okay. So the main aim of the autoencoder is to minimize reconstruction error. What is my reconstruction error? Difference between reconstructed data and original data. Okay. So input space, latent space, and output space data is represented here. And it's called as bottleneck because do you understand the term bottleneck? Everyone, I've seen the bottle, no? What does a bottle look like? The original bottle there only. So the big data suddenly when it tries to comes out, there is a squeeze here. This is the bottleneck. Yeah. So what's the architecture of the encoder? As I said, input layer, encoded layer. What's the other name of encoded layer? It's called as, what is the other name of encoded layers? Yeah, encoder layer, mainly it contains encoder. What does it contain? When you code, when you coded an example, no? What are the layers which are present there? Phonics 2. Sorry. I'm talking about what is encoder layer? What does it contain? Contains dense layers mainly. Okay. And it also contains something else. What is the code here there? I've seen the code. Get the code. So what do you see here? Autoencoder here mainly contains a dense layer. Your decoder also contains a dense layer. So what am I doing here? I'm converting a data input image of 28 cross 28 to 32. Okay. So is the duster? What is happening here? Okay, how does the dense layer will look like? Huh? I have to draw 784, this one. From 1 to 784 and 1 to 32. So each and every point is connected here. Okay, similar to the first point, each and every point will be connected from 784 to 32 to 1 to 784. All will be connected. This is how it will look like. So drawing this won't be so possible practically. So this is a dense layer. All 784 points will be connected to 32 points. Then you will fit the data. After fitting the data, you will get the result. Fitting the data means reducing the error. Okay. So your decoder layer is also a dense layer there. And finally, we have the output layer. Okay, so input layer, encoder layer, bottleneck layer, decoder layer, and output layer. So this is how we reconstruct. And that layer in the middle, the data in the middle, usually it's represented as Z. Okay. If that Z, okay, you vary it. How can you vary the Z? It's not Z code, it's just Z. Some data, it's represented as Z. The middle data or the latent data which is coming there is represented as Z. We have encoder. You are transmitting the data from India. Okay. If you vary the Z, instead of detecting some person's face, giving out a person's face, it will give a monkey face. Yeah. It should have been a person. Usually to represent some, I send some photo of some person. Instead of a person coming out, a monkey is coming out because somebody has manipulated the Z, the latent data which is coming in the middle. Okay. So decoder doesn't know. Whatever input it's got, it reconstruct into this. So this is one of the disadvantages or limitations of your encoder. Anybody plays with the data in the middle. So if I transmit the data from India here, somebody captures it, okay, modifies it and sends it again. That's why it is not used in practical world applications currently. Yeah, even though it has got huge benefits, it's not used because a small bit or small variation in this data, small value data will result in a wrong output. We don't want that. Okay, mainly security purposes. So improper choice of the input to the decoder can result in incorrect generation. So you have to choose Z values or train or construct the encoder and decoder in such a way that you will get minimum loss. Okay. And other than that, you have to look at the distribution of the Z. Okay. You need not have to change the distribution of the Z. Distribution plays an important role. What's the distribution? What do you mean by distribution? Distribution means arrangement. I'm talking about probability distribution here. Okay. What's the probability distribution? Yes. What do you mean by PDF or probability distribution function?
But
See,
encoder layer, which one should I not like something like
example, let's take our heart signals itself. What is the probability distribution of my heart signal? Okay, it will look something like this. What is the probability distribution of the heart signal? If I draw in terms of frequency, okay, heart signal goes from 0 to 50 hertz. That's it. 50 to 60 hertz, not more than that. So if I take 0 to 100 hertz and this is 50 hertz, I'll get a peak somewhere here. This is a distribution. Probability of getting 50 hertz is more when compared to 100 hertz. Okay, probability of getting 50 hertz, I'll get what you call as a Gaussian curve or a bell curve here, something. That is probability distribution. Probability of getting 50 hertz is more when compared to 100 hertz and 0 hertz. That's why there is a peak at 50 hertz. Okay, now instead of hard signal, I will take an image. Okay, I will take an image. Example, I will take a black and white image and draw a smiley. Okay, are they white pixels more or black pixels more?
Black.
Background is in black.
White, background is white.
And right.
White.
White is more. My probability distribution will come in. If I take 0 to 255, my distribution will look something like this. Okay, this is what distribution represents. First was with respect to signals, here is with respect to image. How is image represented? Pixel values. 0 for black, 255 for white. Okay, so we have to check those distributions which are coming in the middle. After encoding, you'll get Z. That distribution has to be verified. After verification of the distribution, you can say, or you can send actually, the verification of the distribution based on its mean and standard deviation values will actually give you variational autoencoders. There's a condition for variational autoencoders. What is that condition? We'll see. Okay. Another limitation of autoencoders are they are not generative models, so they don't define distribution. Okay. You need to choose the latent dimension carefully. Latent dimension means the size of the bottleneck layer. If you choose it in the wrong way, your information might be lost or some other information might come in to resulting in maximum error instead of minimum error. Okay, so this is how it looks like. I'm talking in terms of a person's image. I'm sending a person image at the encoder, and this is what I'll get at the decoder. Do you see any difference between the encoder and decoded output? Because human eyes, even though there is a lot of changes there internally, we cannot differentiate because you're perceiving it as if the both are same. So the important thing is the Z, which is coming in the middle, should be Gaussian. What do you mean by Gaussian? Data should be normally distributed. How does your normal distribution look like? It's a bell curve. How does a normal distribution look like? What will be the mean of a normal distribution? Zero. Take it out. How does your Gaussian signal look like? Google search, don't do ChatGPT. Look at the image of a Gaussian curve or a normal distributed curve. There's a difference between Gaussian curve and normally distributed curve. Okay, what is the difference? What's that question?
It is. Yeah.
What is zero?
Mean.
Mean will be 0 for normally distributed curves and the standard deviation will be 1. Okay. mean will be equal to 0 and your standard deviation will be equal to 1 in normally distributed Gaussian curve. Okay, that's the difference between Gaussian curve and normally distributed curve. So the data which is coming in the middle should be in Gaussian. A standard Gaussian will have mean equal to 0 and standard deviation equal to 1. Standard deviation means variation in the data. Okay, so that's the constraint. And this is how three-dimensional view of a Gaussian curve looks like from the sideways, from the top view. What do you see here? Is it bell-shaped or what? You're looking in 3D. If you convert it to 2D, what will happen? If you cut anywhere, it will look like, horizontally, if you cut it this way, how does it look like? Bell-shaped. Okay, it will look like a bell-shaped curve. There is an isotropic Gaussian. You can see here, where is the mean meeting here? At 0. And the variation is 1, 1, 1. It says standard Gaussian curve. Okay. This is enough. If you know this, you know more half of the mathematics. Okay. So as I said, mean square error plays an important role, or loss function plays an important role here. We have missed half of the mathematics. We'll learn them. Okay. So these are some of the parameters which we'll be playing with autoencoders. The main one is, normal Gaussian curve becomes normal distribution when mean equal to 0 and standard deviation equals to 1. Okay. For normal, mean is equal to 0. Man. See, some things, what we do in mathematics is idealize. Okay. When you idealize it, we say instead of some value, mean equal to some value, we make it 0. We can transform the data actually. That's why it's called a standardization, standard curve. From some value, you make it mean equal to 0. What are you doing? Standardizing. Some given variation, standard deviation, we make it 1. It's called a standardization. What is the standard? Mean equal to 0. Standard deviation equals to 1. That's the standard we are bringing everything to. Okay. So this is a three-dimensional Gaussian curve. So we'll be playing with these 3 parameters. One is the loss function, optimization, and overfitting prevention while creating a autoencoder. Yeah, next will be different kinds of autoencoders. We started with the basic autoencoder. We saw what's a basic autoencoder is, which contains encoder and a decoder, commonly used for dimensional reduction and feature extraction. Next is denoising autoencoder. What do you do here? We remove noise from the input data. Okay, for effective learning of the features. So what we do here, we intentionally corrupt the data and send the data through encoder and decoder. Okay, and let it reconstruct to the original data or the clean data. the encoder and the decoder which you get from that is one of the best autoencoder, which you can utilize later. Next comes the sparse autoencoder. Instead of using all the, we saw now there is a dense network there. From 738, we connected to 32. Okay, instead of connecting all 738, we connect only 600, might be 500. Why? Because it's overfitting. The data is overfitting and there is some error is going for a toss. So what did you go? We go for sparse encoder. This happens for higher dimensional data. Okay, only few neurons will be activated at a time in this autoencoder. So I forgot to mention, in the example we used a dense network, but in some autoencoders we can use CNNs, especially with respect to images. Okay, 2-layer, 3-layer, 4-layer, but the same number of layers should be present in decoder also. It should be a mirror image. Yeah, you won't get the output only. Well, we are not able to reconstruct only because you need to copy the encoder to decoder. No, if you have the same set of convolution networks, okay, it will look something like this. Let me draw it. Example, if you have 512, okay, next you convert it to 256 using convolution network. After 256, 128. Next, 32 suddenly. This is the encoder part. This is how the data is coming. And the decoder part also should remain the same. From 132, it should go to 128, 256, and then 512. Same set of convolution neural network should be there if you are constructing a autoencoder with CNNs. Okay. Here, sometimes what happens when it's overfits, you can skip some of the neurons also. Okay, now next, variational autoencoders, VAE, one of the most popular autoencoders, usually used with GANs. Okay. Example, if you want to generate anything with respect to the given data. Example, let us take OCR. I suppose everybody knows OCR. What is OCR? Optical character recognition. What were you doing there? OCR. What are you doing there? Alphabets. Okay. You are recognizing the each and every alphabets, words, and sometimes sentences. Okay. What are the major problem we faced there was number of input images. We didn't have input images at all to train. So there comes your GAN. Okay. What is GAN? Generative Adversarial Network. We can use GAN as well as your autoencoders to generate synthetic images, variational images, variation autoencoders. We can use to generate variation of images which are generated by GAN. Okay, instead of 100, we can get 1,000 synthetic images and use them to train. So that's the advantage of variational autoencoders. Okay, similarly, the project which was given by Tata Elxsi, forward collision detection system using generate AI. What do they mean by generate AI? Only two things, GAN plus autoencoders, enough. You can generate multiple images of the original image to train the network. Okay. He was given an example where Tesla car was going in the road. Usually in California, what happens? There's San Jose place, and there's one place. Since people cannot pay the rent, they stay around 50 to 60 miles far. Okay. Sometimes they will get saturated in the work, or sometimes they get into their Tesla car, switch into auto mode, and they sleep. It's highway. And the code runs in a far better way. So you need not have to break your head. It will simply go. And after half an hour or something, you can wake up and see, are you in traffic or somewhere else, or stuck or something is happening. But you can get a nice nap for half an hour. Okay, usually people do that. Most of them do that. Huh? You still go. Yeah. You can just give a destination of your house and it will still take you. Okay, and by the time it reaches, it's a destination reach. So what happens? One of the person was going like that, and there was an accident. Okay, the normal trucks means it will be jeep, something like that. It was overturned or something like that, and it was not able to do it because it was overturned, and that caused an accident, I suppose. Anyway, he didn't die. That's a secondary thing. Airbags came out and he didn't die, and he was compensated by Tesla. That was fine. Even though there are 5 to 6 cases on Tesla, none of them succeeded actually. That's a different thing. So the moral of the story is, if they would have used GAN and autoencoders, they could have given different variation of the input image, flipped version, inverted image, etc., and they could have trained it. And the neural network could have recognized it. Okay. So that's where your generative AI comes into picture in the current world. It will stimulate or simulate different variations of the input, or different problems can be given out in order to face them. Okay. So that's the use of generative AI, one of the uses, other than creating different images of you people. What is it? What do you call that generative AI as? Creating an animation of you people. Hmm. Hmm? There are a lot of software, photo editors. There you can create different audios, you can create different videos, whatever it may be. That's not generative AI. Anything which is not there and you generate it, then it becomes generative AI. Okay. It's not there in the real world. Suddenly you give it. Okay. You see, I love have an image with a panda and a cat side by side. It might mix panda and cat together and give you something. Face of a cat and body of a panda. Huh? It will not give the original image. Something similar to that it might give with black and white stripes. Yeah, it will never give the original image. It will be a variation of it. Okay, let us see how this variation comes into picture using variational autoencoder. Okay, so this is an autoencoder. This is how your autoencoder looks like. An input image, reconstructed image, and latent space. Okay, so now what is variational autoencoder? We call it as generative model because it generates variation of your latent space actually. Okay, in latent space, we have some probability distribution. That probability distribution is varied to get something else. As I already told you, no, instead of a human face, you can get a monkey face. How is that possible? Because there somebody has changed something there in the middle. It has generated its own data there. Huh? Pixie, there are a lot of things. Is it a free one? That is the question. None of them are free. Hmm. Filters doesn't come under generative AI. Filter means you are filtering your data. But what happens in that Pixie AI and all, you can see your air and all will be different. It won't be the original. Instead of these classes, it will be something else. So that is actually generative AI. Huh? Yeah, what happens now? It will do detect face. After detecting the face, it will remove your glasses and put something else, or it will color around it. That's it, nothing else. Yeah. But in generative AI, some new things are created actually. New variation of yourself. Okay. So let's look at what are variational autoencoders. So it's a type of deep generative model that learns to represent higher dimensional data in the lower dimensional latent space while being able to generate new data points from this learned distribution. What is the learned distribution coming out here? Z. Vary Z and give it out. You'll get a new thing. That's it. That's your variational autoencoder. Okay, why it is called variational? Because you can vary the latent space. You can vary the latent space. What is latent space containing mainly? Z. What is Z? Gaussian. It's a Gaussian distributed data. So you have some mu value, you have some standard deviation. Vary these two, you get a new data. Simple as that. Yeah. Vary the mean and standard deviation of your distribution, you will get a completely different data after decoding. Yeah, it will be a human being. You would again input for face of somebody else, you would have got an output face of somebody else. That's the difference. What happens there in with GANs is GANs will produce different outputs, and that is passed through autoencoders. Okay, when it passes through autoencoders, you get different variations. Randomly select your mu and standard deviation in order to get a different faces there also. So you're creating a original output. A new synthetic output, not original, synthetic output. Original synthetic output. The autoencoder gives that. You want a synthetic image, you have to go for VAE. Autoencoder reconstructs the original image, but you don't want the original image. You want a different image. Will not go there. Will simply confuse them. Variation of this. Okay. So here also you can see here encoder. This is encoder and this is decoder. A Z is produced and Z is given in order to get the reconstruction. Okay. What is that? The probability distribution function, which depends on your input X. Okay. Yes, man. What is the route? Which project? Okay. Got it. Yeah, you can relate it to your. We're not gone into GAN. We're not into gone into GAN. That's a different concept. I think Afrin has gone through GAN. So what does it do? Okay, we'll see it later. We'll not discuss it. It's not. No, that's not the answer. Okay, so what's the main idea? Vary the Z value here, you'll get a different variations of the input. Okay. So the other way to represent this is this. The encoder computes the distribution P Z of X for any input X. Decoder tries to convert to randomly sampled S from P of Z. What do you mean by random sampling here? Hmm? Look here. What do you see here? See, this is what Z is. Yeah, Z here. Okay. What is the mean value which is coming here? 1 and 0. This is random only. Taking random values of mean and standard deviation as what we are doing. Okay. The latent space output is this Gaussian distributed data. In that, you need 2D output, no? You need a mean value mu and a standard deviation. Take any sample value here. Simple. You'll get a random mu value and a standard deviation. That will give an output. Same top view, you're not there. Top view, side view. I'm cutting here with a mean of 1.
Be like gaming.
All the topics names are.
The random it should be like clustering. Everywhere you see start some parts from it.
Be simplified, be simple always, okay? Okay, always start with ABCD in life. If you do anything, always start with ABCD, okay? Then you build upon it. Okay, simple concept is you'll have some mean value, you'll have some standard deviation. The standard deviation here is more when compared to this point, yes or no? The deviation will be higher here when compared to this. So this is called a sampling. I'm cutting the Gaussian curve here at some point, whichever point you wish. Or I might be randomly cutting it also. This will give you some other output. If I cut it here, it will give me some other output. Each and everything will be a different output. Instead of my face, your face might come or somebody else's face might come. Okay. So this is variational encoder where we randomly sample Z value before passing it to the decoder. Okay. So as I said before, you can see here, theta is the parameter with respect to encoder and your, we call it as, what do you phi. Phi is the parameter with respect to decoder. So both has to be varied in such a way that you get minimum error. Okay, the loss should be minimum. This happens while fitting dot fit in your code. Okay. So encoder takes the input and returns the parameters of probability density, which is a Gaussian curve, which gives some mean value and covariance matrix. Okay. So we are to sample from this distribution to get random values of lower dimensional representation set. We'll sample those values, get some mean value and standard deviation in terms of a covariance matrix and use it to decode. Okay, the input X gives the vector mean and diagonal covariance matrix, determine the Gaussian density. Okay, this input mean and covariance matrix will give you some Gaussian curve. After getting that, parameters theta in neural network need to be learned, need to set up a loss function. Where does theta come? At the encoder. This is the encoder part. In decoder part, it is 5. Okay, this has to be varied. Decoder takes the latent variable z, which is already sampled. Okay, and variable z, and returns the parameters of distribution. Based on the parameters, that is mean and variance, it will produce its own output or reconstruct its output based on the sample data. Okay, this is VAE, nothing else. So loss has to be taken care into picture here. That's very much important while building a VAE. So VAE needs to learn the parameters of two probability distributions. What are the two probability distributions which are coming into picture here? Sorry. Probability distributions at the input xi and reconstruction. Input also has some probability distribution, output also some probability distribution. Input and reconstructed probability distribution should be same. Yeah. I told you, no, each and every signal, if you take a art signal, there is a probability distribution. If you take an image, it also has a probability distribution. So those probability distributions should be same. They are not same, then you got a problem. You need to change theta and phi to make them same. Okay. So this is we have to minimize the expected negative log likelihood. There is a formula for this for loss calculation. What is this? What is this capital E? This is total function. Okay, it is called as expectation. Expectation means average only, not nothing. Average of P phi of x comma xi comma z. Sorry. Negative value might be this log is giving negative output. No, negative into negative will become positive. Yeah. So if you want, I can go to the formulas also, mathematical derivations. Okay, I'll explain it in graphically only. You can see it. So here 3 is taken. We cannot take a dense network here. We have to go for a CNN. Okay. There'll be layers of CNN network. Similarly, if there'll be layers same similar network as I draw here, draw there. What happens? Same set of convolution network in the reverse way in the decoder also. Okay. So what's happening in the middle? That's important. What is M and S? M stands for mean, S stands for standard deviation. We mainly look at the mean and standard deviation of the probability distribution function Z, which is coming in the middle. Okay, and sample it n0 comma I, and sample it to get one sample somewhere in the middle, and that sample is given to your decoder to get the same image as the. Okay, so this is variational auto encoder. That's it. I suppose you are about to finish the assignment there. Yeah. Everyone, assignment. Yeah, auto encodation. And okay, thank you all.